CMOS consists of combining PMOS and NMOS in order to create an overall CMOS gate, which is a combination of the two. So the first thing to understand is what a PMOS and NMOS gate look like. So a PMOS gate will have this circle here. That's the big differentiating factor from an NMOS gate, which does not. And basically, these two are overall components of a CMOS, which combines the two. So if you look over here, you can see the simplest CMOS component, and that is a CMOS inverter. As you can see, there is a PMOS up here and an NMOS down here. You can see this one has no circle. That one's got the circle, so you know it's PMOS at the top, NMOS at the bottom. And in general, this is always the case. PMOS is always going to be closer to VDD, and NMOS is always going to be closer to ground. Another set of terms you might hear used for this is this might be called the drain, and this might be called the source. And then the output of the CMOS will always be between the PMOS part and the NMOS part. So the final output, it's always going to be right in the middle. So as you can see here, it's quite literally right in the middle of the two constituent parts. So you'd have some input voltage that's going in here, and then the final output voltage is going to be right in between the PMOS and NMOS components. So in order to be able to draw these from any given function, the first thing that you should know is what we consider kind of a normal perspective in these problems. So normally, if you're given something that's OR, like A plus B in Boolean algebra, this plus is often used to mean OR, then you want to, in general, in a normal situation, construct a parallel circuit. That makes sense because if you have a parallel circuit, then there are two possible ways that the information can flow through the circuit. It can go either or, and that makes sense because it's an OR gate. If you have an AND, which is often represented by multiplication in Boolean algebra, you want to put them in series in a normal situation. And that makes sense because it's forcing it to go through both gates. You can't take two different paths like you could in an OR. It has to go through both of them, so that's why it is an AND. So in a normal situation, you can use this kind of logic to ration out, okay, in a normal situation, parallel is corresponding to addition, and series is corresponding to multiplication, or and respectively. So with that in mind, when you are given some kind of Boolean expression, some kind of function, like these two examples down here, there's two possibilities. Either all of your inputs are going to be complemented. That means they all have this little hat over here. It means they're all inverted. So this is not x1 plus not x2 plus not x3. Or all of your inputs are going to be not complemented. So here, all of your inputs are normal. This is just x1 plus x2 plus x3. There's a difference in the way that you should implement these two things. If all of your inputs are complemented, you need to treat PMOS as if it's normal. So these guys are going to get treated as if they're normal. Remember, the CMOS circuit is going to be a combination of PMOS and NMOS. So essentially, you draw the function twice. You do it once with PMOS and you do it once with CMOS, and then you connect them and your output is in the middle. So if you see all of your inputs being complemented, then you're going to have to treat this as normal. That means for your PMOS gates, you're going to put them in parallel when you want to add, and you're going to put them in series when you want to multiply. And then you need to know that PMOS and NMOS, they're always opposites to each other. So since we've decided all our inputs are complemented, we're going to treat PMOS like it's normal. That means NMOS is going to do the opposite. So that means that when you want to perform OR with your NMOS gates in the circuit, you're going to have to put them in series. And when you want to perform AND, you're going to have to make them parallel. And again, this goes opposite to the normal that we just defined. And that's because we're choosing PMOS as normal because all the inputs are complemented, and therefore this just has to be the opposite. And in this case, another thing to know here, I know it's a lot of information, is just that whenever you construct a CMOS circuit or a CMOS gate, the output is always going to be put out complemented. So if I were to simply just draw the parallel circuit for this with PMOS, connect it to the series circuit for NMOS for this function down here, and take the output of that, that would be fine. That would be the inverted output because all of these pieces, they would be inverted, and that's the goal with this because they're inverted in our function, so it will properly represent the function. However, if you want to do something like this, where they're not inverted, since your gate is going to by default output, x1 plus x2 plus x3 with all of the parts inverted in this case, right? This is what would happen if I just simply implemented these two things as intended with PMOS being treated as normal. Then you're going to get this being output. And in order to turn it into this, you need to run it through an extra inverter, which basically means you're going to take your output from whatever you did before, you're going to run it through one of these things. It's going to look exactly like this, and then that will be your final output from there. So you have to run it through an extra one of these at the end in order to kind of uncomplement it. So you undo the complement, and that's how you get things that are quote unquote just the way that they were in the inputs, just normal, not complemented. So on that note, if you have none of the inputs being complemented, you get something like this, where everything is just exactly as it is. There's no negations on anything. Then you're going to treat NMOS as normal. That means this time NMOS is getting the normal treatment, which means OR for NMOS is going to be parallel and AND is going to be series. So you're giving NMOS the normal treatment this time because none of the inputs are complemented. And since NMOS is getting the normal treatment, PMOS has to go and get the opposite treatment. So for PMOS in this case, you're going to have to treat OR as series and AND as parallel. So the big things to remember are just that they're always opposite to each other. The normal case means we're treating OR as parallel and AND as series. If we've got everything inverted, this guy gets normal. If we've got nothing inverted, this guy gets normal. And they always have to be opposite to each other. If we ever want to create something for our function where nothing is inverted, then we're going to have to run it through an extra inverter at the end because by default, a CMOS is always going to output the complemented version of your function. So you need to kind of decomplement it by running it through an inverter. And if you want it to be outputted as, all of your terms are inverted here, all your inputs are inverted, then you don't have to go through that extra step because by default, it's going to output everything inverted anyway. So hopefully this makes some more sense when we take a look at some examples. All right, so let's try implementing this function here. We've got x1 plus x2 plus x3 plus x4 plus x5. The first step would be to look at this and decide whether or not our inputs are complemented. Here in this function, we can see that no inputs are complemented. We've got no complemented inputs. And what that means is that we're going to treat NMOS as normal. So this means we're treating NMOS as normal. And what that means for us is that, recall NMOS are these guys. They don't have the little dot on them. And what that means is that for the NMOS part of this circuit, we're going to have addition be parallel and multiplication be series. And since we know that PMOS has to be the opposite, then now we can also tell, okay, for the PMOS part of the circuit, we're going to have addition be series and multiplication be parallel, because this just has to be the opposite of this. And we've chosen this to be normal because we have no complemented inputs. So going from there, we can start to actually draw the gate. So the first thing that we're going to do is we're going to construct the PMOS part first. The PMOS part is always on the top. So the first thing that we're going to do here is we're just going to draw our VDD up here. And then we know, okay, we have 1, 2, 3, 4, 5 inputs. So we're going to have to use 5 transistors. So let's go ahead and do that. 1, 2, 3, 4, 5. So I'm just drawing like a kind of a bump for each transistor. And we're going to draw the lines on them, draw the little dots. So each of these is a PMOS transistor, and we've got 5 of them over here. So now we're going to connect them to our inputs. So we've got x1 through 5. So we can just go ahead and kind of draw that on here. So I'm going to clear this away just for space. So up here we have x1. Then here we x2. We here we have x3, here we have x4, and here we have x5. So this basically completes the PMOS part of our circuit. Remember that I have chosen to draw these in series because we are adding. And since we chose that NMOS is normal, and in a normal situation, series is multiplication, we got PMOS being the opposite, which means that addition is going to be series for PMOS and multiplication is going to be parallel, because these always have to be opposites to each other. And since we're performing addition here, we're going to have to put the transistors in series because that's what we've assigned to addition for PMOS. So for the PMOS part of this, we've put them in series with each other because that's what we've assigned to the addition operation. So now that we've completed the PMOS part, we can go ahead and complete the NMOS part of this circuit. So I'm just going to draw a line down here to connect it to the PMOS part. And now for NMOS, we know we're performing addition. So we're still performing addition here. We still got the 5 inputs. But this time, since NMOS is being treated as normal, that means that our addition is going to be parallel. So we're going to have to arrange these transistors in parallel. So we can just put one there. We're going to need 5 transistors again because we still have 5 inputs. So 3, 4, 5. You're going to connect them all. So these lines go over, but that's okay. All right, and then I'm going to draw the transistors or finish drawing them. So since these are NMOS, they look like this. They don't have the dot like PMOS does. So we've drawn the NMOS transistors, and now we can go ahead and connect them to their respective inputs. So kind of done a bad job drawing this, but X1 is going to connect that way. So you can just connect it off the same wire and connect it there. X2 is going to connect here. X3 is going to connect here. X4 is going to connect here. X5 is going to connect here. So now you've drawn the NMOS part of this circuit. So this is the NMOS part, and this here is the PMOS part. So we can go ahead and connect this part to ground like this in the diagram. And then recall that NMOS and PMOS are always on opposite kind of extreme ends of the diagram, and the final output is always going to come from right in between them. So our final output can come right from here. This is right between the NMOS part and the PMOS part. So if we take a look at this, remember that all of our inputs are not complemented in our expression for F. If we were to take this input right now as VF, sorry, if we were to take this output right now as VF, then we would be getting not X1 plus not X2 plus not X3 plus not X4 plus not X5. That's what we would be getting if we took the output as it is right now. Because by default, these types of CMOS gates are always going to output the complement of the function. So what we want to do is we have to run it through an extra inverter at the end. So if you recall, an inverter is pretty much the simplest component. It's just a PMOS up here, an NMOS down here, and it's just 2 transistors like this. You can draw your ground in VDD like this. You don't have to draw them connecting to each other properly. And then from here, this would be your final output. So you've taken, all of the outputs will be complemented on this wire coming out of the original gate. And then when you run it through the extra inverter, it's going to uncomplement them. And your VF is going to properly represent your function here. So that's how you would draw the CMOS for this function. So let's try this example here now. So again, let's take a look at this. Let's see whether or not our inputs are complemented. Here we can see they're not complemented. So all our inputs are normal. None of them are complemented. So we're going to choose to treat NMOS as normal. What this means is that parallel is going to be addition, and series is going to be multiplication. And then as a result, since NMOS always has to be opposite to PMOS, we're going to treat PMOS as, abnormal, which is going to mean that parallel is multiplication and series is addition. So now that we know how we need to arrange each of the different types of transistors, we can start actually building the diagram. So the first thing that we're going to do is we're going to construct the PMOS part of the circuit, just like we did before. So let's take a look at PMOS. We've got a bunch of multiplication happening here. So we know that multiplication for PMOS in this case is going to be parallel. So we need to arrange our transistors in parallel. So I'm just going to go ahead and draw VDD up here, and then I'm going to draw one transistor. I'm going to draw another transistor, and that should be 4. And again, there's 4 transistors because we have 1, 2, 3, 4 different inputs. So these are our 4 transistors. And since we're drawing PMOS, we're going to draw these transistors. We're going to finish drawing them. And then this is going to connect to some inputs. So let's say this is our X1, this is our X2, this is our X3, and this is our X4. So that completes the PMOS part of this circuit. So we've drawn them all in parallel because parallel is multiplication, since we're treating this as abnormal because nothing's complemented, so NMOS is getting treated as normal. And we've put 4 different transistors together because we have 4 different inputs. So going off of that, we can now try to complete the NMOS part of this circuit since we've just finished the PMOS part. So for this, again, we still got multiplication going on here, but this time for NMOS, series is going to represent multiplication. So we're going to have to put them in series. So we can just draw 1, 2, 3, 4 transistors in series. We're going to connect that to ground. And then we can just complete the drawings of the transistors. And we're going to connect them each to their respective inputs. So let's say this one connects here. And finally, this one is going to connect like this. So now we have completed the NMOS part. And again, this one is going to connect to X1 right here. This one's X2, X3, and X4, and that's just because of the way that we've connected the wires. And we've got 4 transistors for our 4 inputs, and we've put them in series because NMOS is getting treated as normal, and in a normal situation, series is multiplication because it forces you to go through every single transistor. You can't just go through one or the other, unlike when you're in parallel. And then just like before, if we were to, so we know that since we've constructed both halves, our final output's going to come from the middle. So we know that if we were to take the final output exactly as it is right now, if we were to take this as VF, we're going to end up getting not X1 times not X2 times not X3 times not X4. And that's because by default, if we just took the raw output of this, it's going to release the complemented version of our function f. So in order to fix this and correctly represent our function f with none of the inputs complemented, what we need to do is run it through an extra inverter, just like we did last time. So what we're going to do is we're going to connect this inverted output that's on this wire. We're going to connect it to an inverter. So we've got our PMOS part here, our NMOS part there. We're just going to connect them. This goes to ground. This goes to VDD. And then this is our final correct output that is going to correspond to our function f. So this is how you would draw the CMOS circuit for this part, or for this problem. All right, so this example is a bit harder, but let's try to go through it. So let's take a look at our function here. All of our inputs this time, we can see they're all complemented. They're all complemented. And what that means for us is that we're going to treat PMOS as normal. That means that for the PMOS transistors, we are going to have parallel represent addition and series represent multiplication. And since NMOS has to be opposite to PMOS, we know that for the NMOS transistors, we're going to treat parallel as multiplication and series as addition. So now that we know how we should arrange the transistors, let's start trying to construct this. So as we've done before, we're going to start off by making the PMOS part of this circuit. So this is a bit trickier because of the function itself. So let's get started. We've got VDD going up this way. And so the first thing that we should look at here when we're trying to build this is that we've got two big pieces that are being multiplied with each other. And then within those pieces, we have some other information. So PMOS is being treated as normal. So we've got two big things that are being multiplied with each other, which means we're going to have to construct this half of the expression and this half of the expression, and then put those two pieces in series with each other in order to multiply them together. But first, let's start off with constructing this part. So x plus y. How would we construct x plus y? Well, parallel is addition for PMOS since we're treating it as normal, so let's get started with that. So we've just got 1 and 2 inputs are going into this because it's just representing x plus y. So we're going to draw our transistors, and we can connect this to x, and we can connect this to y. So this part here represents x plus y because we've put them in parallel. So now this whole thing, this entire x plus y, we want to put that in series with this other half of it because we're multiplying this whole thing by this whole thing. So we're going to drag this down a little bit. That way we can have this in series with the next part that we're about to make. So now we have to make z plus w times y. So the first step here would be to construct w times y. So series is going to represent multiplication in this case, so we can just put these two inputs in series with each other, or the transistors in series with each other. So let's draw the two transistors. So this part, we're going to connect it to some inputs. We're going to connect it to a W, a W, and this one is coming from Y, so we're just going to connect it to Y. So we can do that. I'm going to actually switch their positions just to make it a bit neater. So that one's coming from Y, and this is coming from a new input W. All right. So this part right here is going to represent W times Y because they're in series with each other. And now we want to add that whole W times Y to a Z. And the way that we're going to add is we're going to put them in parallel. So this whole thing, this whole W times Y term is getting added to our Z term. So this whole W times Y needs to be in parallel with Z. And the way we're going to do that is we're literally just going to put this part in parallel with our new input Z, which we're going to draw here. So this completes the PMOS part of this circuit, and that's because we have our x plus y over here, and we're multiplying that entire x plus y by this whole thing here. And now this part here is going to represent w times y. That's going to be w times y. And this part here is just our z. And so this whole big piece here is going to actually be z plus w times y because we've put those two smaller pieces in series or in parallel with each other. And then these two big pieces are in series with each other. So we're multiplying them together, which accomplishes that multiplication in the middle. So that's how we would do the PMOS part of this. So now with that out of the way, we can start to construct the NMOS part. So we're going to go down from here. And NMOS is going to be kind of the opposite here. So we're going to treat parallel like multiplication and series like addition. So the first thing that we can do is we can try to put together our x plus y. So putting things in series is going to be addition in this case. So we can put x and y in series with each other in order to accomplish this, this addition. So we've got x there, or sorry, we've got y there, and then we can bring x down here. So we got x there. So this part here, this is going to accomplish our x plus y. So now this whole x plus y needs to get multiplied with this whole big term here. So the way that we're going to accomplish multiplication in this case is going to be by putting them in parallel with each other. So let's construct a parallel piece to this. And on this parallel piece, we're performing another addition. So we're going to be adding Z. So we can just create a transistor for Z here and connect that. And we're going to be adding that to W plus Y. So it needs to be to W times Y. So our Z needs to be in series for addition with our W times Y, which would have to be in parallel with each other for multiplication. The way that we can do this is just like this. So we're going to have one for W, one for Y. These two are in parallel with one another. Oh, sorry, they're in parallel with one another to represent the multiplication of the two. And then that whole part is in series with the Z to represent the addition. So we're going to connect this to W, and we're going to connect this to Y. How should I do this? We're going to connect this to Y. We can do that like this. All right, so now that that's connected, we can just put this together and complete that kind of parallel component of the circuit and draw our ground here. And that would complete the NMOS part of this circuit. So here we've got our X plus Y because they're in series with each other. Here we've got this big part in series. We've got our W times Y because those are in parallel. We've got our Z in series with it to add to it. So here we've got our Z plus WY, that whole part there. And then this entire thing, since this half is in parallel with this half, it accomplishes the big multiplication in the middle. So now that we've completed the CMOS gate, we can start taking a look at our output. So our output's going to come straight from the middle of the two pieces we just made. So right between, the PMOS half and the NMOS half, we're going to have our output. Now this time, if we take our output from here, we have the same thing we did last time where everything's going to be complemented, but this time it's not a problem because everything is complemented here anyways. And since all of our outputs or all of our inputs into F are complemented anyway, we don't have to bother running this through the extra inverter. We can just take this output as it is. So in this case, this would be the implementation of the circuit.